Don't hear anything. Anything my phone that good on see. Just so you say, now only money to do, module. I don't joke with me. I can't share one.
Hello. Good afternoon. Hello, can you hear me?
Yes, sir. Yes, sir.
All right. Good afternoon to you all. So you're welcome to AMS 102 class. Today is our inaugural class, and that means it is time for me to introduce the course content, the learning objective, and the course materials. So my name is Professor Adeleke. I'm the course coordinator, and I will be taking up AMS 102 along with other lecturers. So I want us to please mute ourselves. Please, can I mute ourselves? Am I forced to eject some of us? Please, kindly mute. So the course title is Basic Mathematics, and the total number of units is 2. We have 7 of us that will be taking the course. I myself, Professor Adeleke, I have Dr. Ele Ajijola, Dr. A.B. Shogunro, Dr. G.C. Mesike, Mr. A.C. Mungu, Mrs. Lamide Patrick, and Mr. Ismail Eboda. The 7 of us are from the Department of Finance and Insurance. And the course description as displayed. Basically, the course will cover the preliminary phase of algebra and calculus. So, starting with number systems and ending it with definite integral. So, the learning outcomes, amongst others, include ability to identify basic concepts of mathematics and appreciate its application to business. So I will suggest if we can get copies of mathematical methods for business economic finance published by McGraw-Hill. You can get the latest edition if you can. Maths book that covers the topic can also be used. So what you have on the screen are the assigned topics to each of the lecturers. So we'll be teaching in turns. Derivative will be taught by Mrs. Patrick. I will take you definite integral. Number system will be taken by Mr. Eboda. Same sequence and so on. So we are supposed to teach you from May 27th, last week, and we'll end our teaching by July 10. Before exams, lecturers that missed their classes due to one reason or the other can make arrangements after that 10th of July. So the assessment, your nurse assessment will be between 30% and 40%. And the results for the continuing assessment will be displayed and will be known by every other person before the exam date. So please ensure that you participate in the continuing assessment, which form in form of a test when the time comes. So this is how we are going to manage the class, and I wish you guys the best. So I want to confirm if you all received the materials on the integration I shared this morning.
Yes, sir.
We did, sir.
So I'm sure you received this material. The material is a 48-page document that explained the concept of integration and also extended to different methods or techniques of integration, and I ended the material with double integration. Majority of all did further math at school, and you must have come across differentiation. And the function that reverses the process of differentiation is what we'll be dealing with here, and that is our integration. We all know that if you have a function, say x to the power of n, and you differentiate it, the derivative will be n times x to the power of n minus 1. So which means that the power of the x will be used to multiply x, and then the power will be reduced by 1. So what if you are interested in deriving a function that was actually differentiated to produce nx to the power of n minus 1? That means you want to reverse your process that produced that derivative. That reversal is known as anti-derivative, and it's also called integration. So I want us to have a look at the function that we have on the screen. So we have a function x cubed to the power of 3. X cubed to the power of 3. And ordinarily, if you are to differentiate this function, you will get the 3 that you have at the power will multiply that function. So when it multiplies it, it becomes 3x, and then reduce the power by 1, and that gives you 3x squared. Since the original function is being divided by 3, the derivative will have been x squared, just as we have here. You can see that I had differentiated my x to the power of 3 over 3 to give x squared. Now, what if I have a constant that was added to the function that I'm integrating? So remember that the differential of a constant is 0. So the constant, for example, if it is 2, if it is being added to x cubed to the power of 3, the differential will still be x squared. Even if the function is pi is a constant. So if I use that to my function, which is s cubed of, if I differentiate, I will say end up getting my x squared. So even if I have it as root 5, so generally the function has a constant attached to it. We can have it in the form of x cubed divided by 3 plus c. So if I differentiate that, I will get x squared. So if I'm to reverse the process that gives me x squared, the process, that is the reversal, should result to the original function, which is x cubed to the power over 3 plus c, because that's what it should be, where that c represents any constant. So, and that is the idea behind integration, which is a reversal of derivation, or simply put as anti-derivative. So if you have x squared all over 2, the differential will give us x, just as we have here. Why is it x? The power we use to multiply the function, and then you reduce the power by 1. And that should be 2 times x to the power of 2 minus 1 all over 2, okay? So when you divide, you have x. So similarly, if you are to differentiate x to the power of 3, you will have 3x squared as your derivative. Here, there are no constants added or subtracted from x squared over 2 or x cubed. So if you are to reverse it, the reversal should produce the exact function that you differentiated earlier. So there are standard formula for defining integration or anti-differentiation. So the first one is the integral of the function f of x being defined as capital F of x plus c. The integral is the symbol that looks like this elongated s. That is the integral sign. The function that you are integrating is our f of x. Okay, and then you are integrating it with respect to x, and that's why you have it as dx. So if you integrate that function, it gives you capital F of x. So that means if you differentiate capital F of x, it will reverse you back to small f of x. So the relationship between the capital F of x and small f of x is that small f of x is the differential of capital F of x, and capital F of x is the integral of small f of x. That's the relationship between them. So if you see an expression that is written and that function that represents it is actually capital F of x, then you know, oh, a function has already been integrated to produce that. But if you have it as simple f of x, not capital F, then it means that the function might have been integrated, okay, to get that small, might have been differentiated to get that small f of x. So you can reverse, okay? You can move from capital F of x to small f of x by differentiation. And you can move from small f of x to capital F of x by integration. So generally, if you have a function written as x to the power of n and you are integrating it, that the integral will be that you will increase that power by 1, and then you divide the new function by the power that you have. So look at it, we are starting with x to the power of n. If you increase the power by 1, it gives you x to the power of n plus 1. And then that power of n plus 1 will be used to divide the function. And then you add the arbitrary constant c. C that was added will represent any constant that might have been differentiated in the first place. So remember, I illustrated with the constant pi, root 5, and so on. That as long as it's a constant, if you differentiate it, it will be 0. So if you have a function that's already been differentiated and you want to reverse it, then it means that there's a possibility of a constant that must have been differentiated to 0, and that is where constant C is coming from. The second result is that when you integrate an exponential function, as long as that x does not have a coefficient, then you will get back your exponential function. The fourth one, if you integrate a reciprocal function, 1 all over x, get logarithmic of that function plus constant C, provided that what you are dealing with is not 0. Remember, 1 all over 0 is undefined. So if you have an undefined function, it will be near impossible for you to integrate that function. And then if you have log x, the integral of log x is x log x minus x plus the arbitrary constants. So what you have are the results of integrating a function if you have them in different forms as being displayed. So even if you have a compound function or you have composite function, you can also integrate. Consider the results in number 6. I have two different functions, f of x and f and g of x. The two functions can either be adding to each other or subtracting from one another. So to integrate them or to integrate the function, you can separate f of x, g of x, and then integrate separately. After which you add the result. So f of x can be maybe 2x, and f of x can be maybe 3x or 3x squared. So if you have 2x, so if you have 2x added to 3x squared and you want to integrate, so what that number 6 is suggesting is that you will integrate your 2x and also integrate your 3x squared. At the end of the day, you add up your results and you can add the arbitrary constant C to it. So let's have a look at different examples. I'm integrating 5. 5 is the same as 5 times 1. And it's also the same as 5 times x to the power of 0. So if I integrate x to the power of 0, it should give me x to the power of 0 plus 1 divided by 0 plus 1. Then I will add arbitrary constant C. So that means x to the power of 0 integrated will be x. And if we use that to multiply 5, that gives you 5x plus your arbitrary constant C. So the same 9x. You all know that from the result, displayed here, that if you integrate exponential x, we will end up getting exponential x. So for 9x, for 9 exponential x, if you are integrating, you can bring out the 9 or you factorize. So you have 9 times the integral of exponential x with respect to x. So the integral of exponential x will give you exponential x. Of course, multiply by 9 will give you 9 exponential x plus the arbitrary constant c. So also you can look at example D. The example D has several functions multiplying to each other, adding to each other. 4x cubed is a function. 2x is also a function. And 1. So, and that is from our result 6. And the easiest way to sort out this is to integrate each of the functions separately, and then you add up the result. And that's what we have here. You integrate your x cubed, integrate 2x, and then integrate minus 1. And at the end of the day, you have your result. So, and more examples are there for you to work with and solve as many questions as possible. So, and I also have some other exercises I was not so, I would advise that you lay your hands on them. Methods of integration. So we have integration by substitution. Integration by substitution. But meanwhile, if you have questions, please, you can always raise your hands and we will attempt to your question.
Thank you.
Integration by substitution. Method is appropriate when you have two functions multiplying each other, such that one of the functions is a differential of the other. I'll take it again. Integration by substitution. I have two functions, f of x, I have g of x. And I'm multiplying them together. If f of x is a differential of g of x, that means if I differentiate the whole of g of x or differentiate part of g of x, the results will yield my f of x. Then integration by substitution will work. Now let's demonstrate with the example on equation 2 as being displayed. I have x squared. That's a function, call it f of x. Exponential x cubed minus 1. Call it g of x. But I notice that if I differentiate x cubed minus 1, I will get 3x squared. I integrate 3x squared exponential x cubed minus 1. But I notice that the function of my g of x, which is x squared minus 1, if I differentiate it, it will give me my f of x. my f of x here is 3x squared. So since a function of my g of x, when differentiated, produces my f of x, then integration by substitution will work. Now, so now someone was raising his hand. Please, go ahead. Ask your question, please. Need to ask your question. All right, maybe. So, let's see how it works. Remember, I noticed that if I differentiate a function of my g of x, produces my f of x. My f of x here is so I will now substitute my 3. If I substitute it as a function, then I can easily make you the subject. So I will share a plain document now, and then I will work out some of these functions. Just hold on, please.
Ah,
Okay. Let's see. So let's assume we have a x equals 3x to the power of exponential. Okay, so this is the function, and you want to integrate this. So given that f of x equals to this, yeah,
Subpart. Knowing not starting his own, I just take that one start from body class. I see.
so you have to integrate small f of x dx,
Yes.
and you noticed. So you notice that
I don't know why are people suspecting that this like that adopted son. Why is
no, and people agree with me that the differential of x cubed minus 1 will give us that. And that suggests that integration by substitution will work. What we do is that we let our introduce variable, call it u. Let u be equal to this u be equal to x cubed minus 1. Then we will differentiate u with respect to x. Then du dx will be equal to 3x squared. So we can make du the subject. So if you make u subject, you will have our du to be equal to 3x 3x squared times dx. Okay? So what it means is that I can now go ahead and substitute. And this implies remember that to integrate this. So this will be the integral of this will to the integral and rearrange. So do you agree? I cannot rearrange, but see x squared dx is du. Can you see it? 3x squared dx is du. So, which implies after substitution, we will have integral, the whole of is u. Right?
What if I say I love you? I don't want to know. If you play me, just keep me on the low. The mic man is Chris.
How far wait till they do you now?
As the class ended,
They play like us. Them no fit.
eh?
Them no fit give una small chance. Sha, just one chance like this.
Kí ló ṣẹlẹ̀, kí ló bọ́ bí? Kí ló ṣẹlẹ̀, kí ló bọ́ bí? Kí ló ṣẹlẹ̀, kí ló bọ́ bí? Kí ló ṣẹlẹ̀, kí ló.
Shey na 2 minutes wey lecturer use comot na I no wan dey craze.
Blessing. Make una calm down now. Wetin dey do una? Ṣépè sí pẹ̀lú dáadé. E no go better for the lecturer. I be the man.
Hey, your magic number, you are playing. Okay.
Where lecturer go now?
I don pursue the man abi.
I'm gonna make lecturer come fast. I get what I want to do.
I be class doing.
Everybody leave. The class has ended.
I bet Mona explain that to me lecturer. Just explain finish now. Mona explain them again for me.
Everywhere just blow. I never understand anything. I just dey look wetin the man does the talk to.
Why must go there online? Why must go there online? It don't make sense.
Like if you want to understand this thing, make the class dey physical, I swear.
As for
I forgot to have it. How you use the alcohol?
See on the chatting for
My dear, let me just save now. Yeah, right. You see me live with you there. It's my OG. That's my OG. Congio, who help me? Congio.
you know that data dey expensive now.
Hello.
No get sense. Come, read this one. You are hungry.
I'm leaving.
Everyone can leave the class. The class has ended. Professor Adeleke is having issues with his network, so he'll reschedule the class. Everybody can exit now. Thank you.
Everybody get the fuck out of the fucking class.